Hi, guys. How you guys doing this morning? Yeah. Good. I'm doing good too. I can't believe we're actually wrapping up the semester. It's kind of wild. I mean, it always takes me by surprise at the end that we're, basically finishing up all of our material. Just as a reminder, today I'm going to go over the last couple examples for chapter 3.2. These come from a couple of final exams. And I just want to go over, and they have absolute value stuff in them. So I wanted to make sure that we're on the same page about how we think about absolute values and what we do. Also, I hope you guys have a chance to see on our modules page for next week. I've posted about 5 different old final exams for this class. I think most of them have solutions. I think the most recent one from the spring semester, I don't have a solution set for it, but I'll come up with one. I'll do it myself and then maybe post it over the weekend. Please take a look at those next week, Monday and Tuesday. Those are class periods for us, kind of like glorified office hours, where we're going to go over the homework for 3.2, so we're on the same page about how we do that. And then because the homework for 3.2 is due Monday night, and then we'll go over all of any questions that you guys may have on the old final exams. If you haven't really had a chance to look at it, or if you're kind of shy, you haven't thought about it, I'll probably pull some example problems from the different exams and then talk about how to work it through and then strategies and all that. But please come prepared for questions or just to take notes. And then definitely I'll post those videos onto our classroom page. Anyway, I think that's about it. So today what we will do is we're going to go through these 2 example problems from chapter 3.2, and then I'll open it up to questions that you guys may have on homework for chapter 2, 2.1, 2.2, 2.3, 2.4. We have a quiz today. Okay, this is our last quiz. And anyway, that'll open up at noon today. So let me go through these 2 problems here for 3.2, and then we'll start talking about homework stuff. Okay. All right. Phew. Okay, so let's talk about this. So what we have, these 2 problems are from old final exams, and they're more about like area, area, in the graph, but they have absolute values on them, and I wanted to make sure that we covered them. So one of the things that we need to ask ourselves, if we see an absolute value question, we have to ask ourselves where on the graph, like if we didn't have the absolute value, where would that graph be negative if we didn't have the absolute value? So let me just write that down. So where would this function be negative if we didn't have the absolute value? We're going to do it a couple of ways. We're going to graph it so we can see it visually, but we're also going to solve it algebraically too. And so then you can see that, because the process by which we take the absolute value is to identify the area of that function that's negative and multiply it by a -1. If I multiply a negative number by a -1, it makes it positive. Okay, so that's how we're actually going to be working that. So what I'm going to do here is I'm going to plot this out. So give me a sec. So this is in vertex form. So our vertex is 2 minus 4. So 1, 2, 3, 4, 5. That's our area that we're integrating over. 3, 4. So 2 minus 4 is our vertex. Now I need to figure out where this thing is going to pass through the x-axis. So the first thing I'm going to do is I'm going to FOIL that out. And then I've got the -4. And then I'm going to set that equal to 0 and solve for x. But let's go ahead and do that. So x squared minus 2x plus 4 minus 4 gives us x squared minus 4x equals 0. So we're going to solve for x, right? And this is going to be x minus 4 equals 0. So x equals 0 and x equals 4. So it passes through the x-axis 1, 2, 3, 4, here and here. So I've got a parabola that goes like this. Okay, so let me draw it in green. This is a dot. So let me draw it in green. So this area here is the function without the absolute value. So with the absolute value, what happens is this part becomes positives. 1, 2, 3, 4, 2. So it goes like this. Okay, so the part that we're actually looking for, the area under this curve, is going to be, we're going from 0 to 5. So I want this stuff. And I want this stuff. This is the area that we're looking for. Okay, so the whole process that we do that, okay, is going to mean I need to identify the region between 0 and 4. I have to make that positive. The region between 1 and 5, between 4 and 5 is already positive, so I just leave it alone. So let's do this. I'm going to say we're going to negate region between 0 and 4. This will make it positive. Make it positive. And then we're going to leave positive the region between 4 and 5. So what we're doing is we're breaking up our integral into two pieces, right? I'm going to go from 0 to 4 and then from 4 to 5. Because 0 to 4 I have to make positive, and then 4 to 5 I'm going to leave alone. So let's go ahead and do that. So what I say is negative. I'm going to go negative. I'm going to integrate from 0 to 4 of this function here. So I'm going to go like this. X minus 2 squared minus 4 dx. Plus, I'm going to add in the rest of it, 4 to 5, x minus 2 squared minus 4 dx. Now we already FOILed this out, so we know what this is going to look like. It's going to look like that. And I need that because I'm going to integrate it, right? I'm going to do the power rule. So let's go ahead and write that out. So it's going to be 0 to 4. Where am I? X squared minus 4x dx plus 4 to 5, x squared minus 4x dx. Okay. Now we need to do is we have to distribute the negative, but watch, be careful, because I have to distribute it to this term, which is going to make it negative, and then this term, which is going to make it positive. Right. So let's go ahead and do that. So then I'm going to get 0 to 4 minus x squared dx minus 0, I'm sorry, plus 0 to 4, 4x dx plus 4 to 5. This stays the same, x squared dx minus 4 to 5, 4x dx. Okay, and when we go to integrate this, we're just going to do the power rule to integrate. Okay, so that means I'm going to get, right, this is an x squared. Okay, so when I go to integrate this, yeah, I'm going to get, let's see, minus 1/3 x cubed, right? This is a plus. This is going to be 4x squared over 2, so that's actually just 2x squared, and we're going from 0 to 4. Okay, plus the other bit, this is 1/3 x cubed minus 4x squared over 2, 2x squared, and we're going from 4 to 5, that's a 4. Okay, so what you guys need is, to do this, you need this line, and we need this line, our antiderivative, okay, to show that you know how to set things up, you know how to negate it, and you know what the antiderivative is. So let's go ahead and do our fundamental theorem of calculus and then figure out what that area is. So I'm going to go, my first bit, so I'm going to go minus 1/3, this is 4 cubed, plus 2, 4 squared, minus, we're going to do the 0. I'll plug in the 0 so that you can see the fundamental theorem, even though it's going to come out to be 0. Minus 1/3, 0 cubed, plus 2, 0 squared. Okay, so that's this part plus this part right here. 1/3, 5 cubed, minus 2, 5 squared, minus the 4 part now. 1/3, 4 cubed. Where am I? 4 cubed minus 2 times 4 squared. Okay, fundamental theorem of calculus, I'm just gonna like multiply out all the numbers. It goes to 0 right here. Multiply out all the numbers and combine everything. And then in the end, what I get is my area between 0 to 5 is equal to 13. So that's how we handle an absolute value. And I guess technically, maybe these questions are maybe more for chapter 2, which is like a definite integral. But I thought, with the absolute value, we need to be able to think about what we have to cover for that. Okay. Sometimes these are called area in the plane questions, but because the absolute value makes it different. All right, last question. And by the way, there's a typo. These last 2 questions we already did in the previous, so I'm going to get rid of those. These come from a previous page. Okay. All right, so let's take a look at this one. This is also from, it's a final exam from the 2015. And again, we have an absolute value that we need to deal with. So we're going to integrate from 0 to 5, absolute value of 2x minus 2. So again, we have to ask ourselves, where is this function negative, like below the x-axis, without absolute value. Okay, we're going to graph it and then we're going to do it algebraically too. Okay, 1, 2, 3, 4, 5. We're going from 0 to 5. Okay, so if this were just a regular equation, 2x minus 2, my y-intercept is minus 2. So I'm going to go 2x minus 2 equals 0. I'm going to solve for x. X is equal to 1. So it passes through here. So this gives me, oops, I didn't draw that very well, sort of a range of what I'm doing. Now this is the part of the function that if we didn't have the absolute value, so there's our function. You guys see that? It looks a little blurry. Function without the absolute value, right? And now what we need to do is we have to make this absolute value makes that part positive. So that would be up to here, and the function's actually going to go like that. Okay, so that's with the absolute value. So that means that the region that we're going to be integrating from 0 to 5, start here, go here, 1, 2, 3, 4, 5. Let me draw this up a little higher. This region right here. Okay, so this is the region that I'm going to be integrating. And I'm looking for the area for this part and this part. Now the trick is, because it's an absolute value, I have to break up my integral into 2 pieces, going from 0 to 1. I have to make that multiply by a negative number. So those are negative values. Multiplied by a negative number makes it positive. This part here from 1 to 5, I leave as is because it's already positive. Okay, so let's write that down. So the region between 0 and 1 gets multiplied by -1 to make it positive. And then the region between 1 and 5 stays the same because it's already positive. Okay. All right, let's do it. Okay, so between 0 and 1. So I'm going to break this up. I'm going to go negative, integrating from 0 to 1, my function, 2x minus 2 dx. Plus, I'm going to integrate from 1 to 5, the same function, 2x minus 2 dx. So we wrote it in words what we're doing, and then we did it in math, right? So let's go ahead and distribute this negative to this and to this. So you have to be careful because it's going to make this term positive, okay? All right, so let's go ahead and do that. So it's going to look like 0 to 1 minus 2x dx plus 0 to 1, 2 dx plus 1 to 5, 2x dx minus 1 to 5, 2 dx. That minus comes from this equation right here already, okay? So this is, we'll just rewrite this again. We're going to take out the constants. X dx plus 2, 0 to 1 dx plus 2, 1 to 5 x dx minus 2, 1 to 5 dx. Okay, so now we're just going to do the power rule again. The hardest part in these is the setup, right, where we're trying to figure out which region is positive and negative and what do I have to do with that. Okay, so let's go ahead and do this. So this is going to become minus 2 times x squared over 2 plus 2 times x, and we're evaluating that portion from 0 to 1. Right, now this part plus 2 times x squared over 2 minus 2 times x from 1 to 5. I'll rewrite this. This is minus x squared plus 2x from 0 to 1 plus x squared minus 2x from 1 to 5. Okay, now we'll do the fundamental theorem of calculus. Okay, so basically, by the way, what you need to get full credit is that line and that line. Okay, the rest is like, sorry, the rest is kind of just like, you know, general algebra stuff, but you need to show the setup and you need to show what the antiderivative is. You probably need to show that you can identify the regions where it's positive or negative. I did it graphically and sort of, you know, algebraically where I can see where it's going to pass through the axis. If I didn't want to do it graphically, I can also get this point here and then test the function, choose values within this range, you know, within this range that are less than 1, choose values that are between 1 and 5 and see what kind of, do I get positive or negative, and that'll help me out too. That's another way of doing it algebraically. So let's go ahead and evaluate this. This is going to be minus 1 squared plus 2 times 1 minus, let's do the 0 even though we don't need it, minus 0 squared plus 2 times 0. We don't need it because it's going to be 0. So that's the first bit, plus our second bit, we'll do 5 squared minus 2 times 5 minus 1 squared minus 2 times 1. Okay, first interval, second interval, right? So I can add them all together, and in the end, I'm going to get the region under that graph is 17. Okay, absolute value is always kind of a trick, you know, how you think about what you need to do. But when you're trying to integrate an absolute value function, right, you look for the areas where that function would be negative, right, the area below the x-axis, multiply that region by -1 to bring it, make it positive, and then you can just then integrate it. All right, folks, so that's basically it for 3.2. What I'd like to do is I'll scan that in and I'll put it up on our Canvas page later today. And if you guys have any questions on homework problems, I'm happy to answer them. Remember, we have a quiz today on all of chapter 2 in the Integral Calculus book. So let me know what you have. I'll look in the chat or you guys can say it. 2.3. Number 39, sure, let's take a look. Okay. Okay, yeah, that's an interesting question. This is kind of like a trick. So let's see if I can get this in focus. It's not focusing. I'll try it again. So this is chapter 2.3, question 39. I hate it when it doesn't focus. Give me just a second. Trouble with cameras today. No, it's better. Okay, so what we're looking for is the signed area between the graph and the x-axis. And we're going to go from -5 to 5, and we're looking at radical 25 minus x squared plus 4 dx. All right, so let me just plot this out here. So this is like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, our bounds for integration. So this right here, plus 4, so this is essentially that, let me go this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so what happens is we're shifting things up by 4, right? But this right here is a half of a circle. Like if you weren't sure, you can plot this out too. This is, you are allowed to use your graphing calculator, so you don't have to try to figure it out. Like, what does this look like? So 25 minus x squared, and then plus 4. Okay, so our graph looks like this. This is the function, radical 25 minus x squared plus 4, and I graph it out. Okay, actually, let me change the window a little bit. Y-min, I'll make that Y-min to 0. Okay, so we're up to 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going out to 5. 1, 2, 3, 4, 5. So it comes down to, let's see, 2, 2, 4 to here, 2, 2, 4 to here. So this is a half a circle. And then basically we're looking at doing this region here. I'm not drawing this very well. It's really supposed to be a circle. Okay, so that's the area that we're looking to integrate, okay? Because it's between that function and the x-axis. All right, so let's think about our tools for integration. Let's see, I can't just integrate it as it is. Use substitution maybe, let's try. So if I say u is 25 minus x squared du is equal to minus 2x dx. Well, I have a problem, right? Because all I have is just dx. I don't have an x dx in here somewhere, okay? Which means I can't integrate this. So this is like a trick question. Not integratable in current form. We're going to learn in Calculus 2 other methods for being able to integrate this, but we can't do it with the tools that we know right now. So not integratable in its current form, so that basically means cannot use substitution. And this is a case where you could do things like Riemann sums, right, to get the area under the curve, or you can do, next semester, we're going to learn things like a polynomial approximation for a function. And then those are ways that you can actually use to integrate this function here. But we can't use any of the methods that we know so far about integrating. So we can't use substitution because we don't have any way of making that actually work. So we have to use geometry. And the geometry that we use breaks up like this. So I've got a half of a circle, right? There's a half circle. And then I have a rectangle. Okay, so we're just basically going to be adding up the areas, like half circle, like the area of a circle divided by 2, and then the area of a rectangle. So, so rectangle is, base times height plus 1/2 times a circle. Okay, which is 1/2 pi r squared. Okay, so our base, right? The base on this is going from -5 to 5, so our base is 10 units. And then the height on here is, this is up to 4. Plus, right, this is 1/2 pi. And then the radius on here, we go from our general, this is our radius here. So this is going to be like square root of 25. So our radius is going to be basically radical 5 squared. I'm sorry, did I say radical 5 squared? Not radical 5. I just meant 5. Radical 25 squared. Five squared. Okay, and that came from this equation here, 25 minus x squared. So whatever this term is, I take the square root of, and that gives me my radius. All right, so right now we just plug it in and work it out. So that's 40 plus 1/2 pi times 25. And then, you know, I can plug this in and actually get a number using pi, my pi button on the calculator to get 79.27 as an area. But you had to use geometry for it because we couldn't come up with, we can't integrate it. You'd have knowing that with the tools that we have right now. 2.4, 23, and 24, sure. Okay, you guys all set with this one? I'll let you finish writing that and then I'll scroll up to the next one. So this is chapter 2.4 and we're going to do question 23. Okay, so question 23 says, what's the area under the graph? Y equals 3e to the x plus 2, and we're going to go from 0 to ln of 7. Okay, so that means I'm going to set this up as 0 ln of 7. ln of 7 is just a number, right? I can plug it into my calculator and get some decimal, you know, stream out there, but I'm just going to leave it as ln of 7 because we're going to plug it into e to the, you can see e to the x, e to the ln. All right, so I'm going to go 3e to the x plus 2 dx. Okay, so I can plug that in. I can do my linearity 0 to ln of 7, 3e to the x dx plus 0 ln of 7 2 dx. Now I can integrate this. So I've got the 3 as the coefficient that carries through. My integral of e to the x is just e to the x. This is going to be 2 times dx. This becomes 2x, and we're going to go from 0 to ln of 7. Now I do the fundamental theorem of calculus where I say 3 e to the ln of 7 plus 2 ln of 7 minus 3e to the 0 plus 2 times 0. Okay, so let's go ahead and do this. So 3e to the ln becomes 3 times 7, right? Plus 2 ln of 7 minus 3e to the 0. 3, well, e to the 0 is just 1, so that's minus 3, and this is 0. Okay, so basically we've got 21 plus 2 ln of 7 minus 3, which is going to give us 18 plus 2 ln of 7, which is like, you know, approximately 21.89. You can leave it like this, or you can come out like that. Either way is fine. And 24. All right, let's see. Okay, you guys got this? I'm gonna turn the page here. All right, so chapter 2.4 question. Sorry, question 24. All right, so this one, I've got the area. I actually, let me just see what the exact question is because I have it written down in a funny way. Give me just a sec to get the homework out to see the exact question. 2.4. And we're dealing with chapter repeating the graph of y equals this in the interval on the x-axis. So in positive, you need to calculate the total area both above and below the given interval. So it looks like they want like a they want the area, not the signed area, but they want the the area. So like we have to figure out where regions are going to be positive and negative, and then we have to make the things that are negative into positive parts. So I've got y equals minus 2 plus 3 over 1 plus x squared minus 1 to 1. So basically what we're going to do is we're going to integrate from minus 1 to 1, the absolute value, right? Because they want us to be able to come up with just the total area, not the signed area. They want us to figure that out. So let's do this. Let's just kind of take a look and see what it looks like. So I'm going to go minus 2 plus 3 divided by 1 plus x squared. And I'm going to graph it. And I need to change my window. Okay, so I'm looking at this as my graph. So I'm going to go, let's zoom in a little bit more. Minus 3, 3. Okay, so the area that I'm looking at from -1 to 1, right? This is the area. So it's going to look like, and here's 1. So I'm going to come up just beyond that. And then just before it. Right, so this is what I'm looking at that we want to integrate. So we need to identify this region right here and make these regions positive because we want to be able to integrate that whole area. So I need to go like this. This is what I really want to be able to figure out what's the area for. Okay, so we're going to take the absolute value of that because they told us they want the total area, not the signed area. All right, so what I'm going to do is this. I'm going to say -2 plus 3 over 1 plus x squared equals 0, which becomes 3. And then I'm going to solve. I'm going to cross multiply and solve. So this becomes 2 plus 2x squared equals 3. I'm going to subtract 3. And then basically, no, I'm sorry, I did that wrong. I'm going to subtract 2 minus 2. So I'm going to get 2x squared equals 1. So x squared equals 1/2. So x equals plus or minus radical 1/2, right? 1 over radical 2, which is like plus or minus 0.7071, just to kind of let you know like where it's passing through. Like, so right here, that's 1 over radical 2. So this is how we're going to break it up. So our bounds are going to go from -1 to 1 over radical 2, and then from 1 over radical 2 to positive 1 over radical 2 to this area here, then we're going to make that negative. So we've got these, I'm not saying this very well. From here to here, we have to multiply by a -1. And then from here to here, we have to multiply by a -1 on our integrals. So we're going to have 3 intervals, 3 different integrals that we're going to be working with as a way of making sure that we're getting the positive values here. All right, maybe I'm not explaining that very well. Okay, so we can also tell, let's plug it in. So if I plug in a -1, this is algebraically, right? So if I plug in a -1, I'm going to get -2 plus 3 over 1 plus -1 squared, which is equal to a positive number. Y, I'm sorry, that's equal to a negative number. Y at 0, which is -2 plus 3 over 1, essentially is a positive number. This is how we do it algebraically. Y at, say, +1 -2 plus 3 over 1 plus +1 squared is going to also give me a negative number. So this kind of tells me that the function's negative, and then the function's positive in these regions. So if I can, like, I'm basically figuring out numbers within these regions here. So I'm going to go from -1 to -1 over radical 2 as one interval. I'm going to go from -1 over radical 2 to positive 1 over radical 2. And then I'm going to go from positive 1 over radical 2 to 1, right? These are my 3 different intervals for integrating, right? Only this region is negative, this region is positive, this region is negative. So I have to multiply this by a negative number, multiply this by a negative number in order to flip those regions to be positive. So let's go ahead and set that up. So it's going to be -1 to -1 over radical 2, this function here, -2 plus 3 times 1 plus x squared dx, plus, this is the positive region, -1 over radical 2, 1 over radical 2, -2 plus 3 over 1 plus x squared dx, plus, and we have to do a minus 1 over radical 2 to 1, -2 plus 3 over 1 plus x squared dx. Okay, so this is our integral. This is what we need. This is what we need, right? And now we have to figure out our antiderivative. All right, so there's some math going on here, some algebra. All right, so it's basically going to be -2 dx plus 3 times 1 over 1 plus x squared. So I distributed these numbers here, let's see, this is minus minus, this becomes positive, that becomes negative. Plus, this is a minus 2 dx plus 3, 1 plus x squared dx. Minus minus becomes positive. Minus 3 over 1 plus x squared dx, right? And so this is our first region, second region, third region. So minus 1 to minus 1 over radical 2. Minus 1 over radical 2 to positive 1 over radical 2. And this is 1 over radical 2 to 1. Okay, I just distributed the negative. Okay, now we're going to do it. So this is going to give me 2x minus 3. So 1 over 1 plus x squared. It looks like, oh, how am I going to integrate that? You have to remember that that's an inverse trig function. Okay, so this is going to be inverse trig there, and this is going to go from minus 1 to minus 1 over radical 2. Okay, and then I'm going to go plus, I've got this, let's do it like this. And then I'm going to get minus 2x plus 3 inverse tangent of x, and that's going to go from minus 1 over radical 2 to 1 over radical 2. And then plus same thing, right? We're doing all the same stuff. So 2x minus 3 inverse tangent of x, and that's going from 1 over radical 2. Can you guys see that? 1 over radical 2 to 1. Right, it's a lot of work. And then you can make sure you're in radian mode if you want to plug this in to get like an actual number. You're going to need this. This is your antiderivative. Okay. And then our answer is approximately equal to 10.44. I'm sorry, 4413. I plugged it into my calculator, but make sure you're in radian mode when you do that. Phew. The hardest part was the setup on that one. 3.2, you want to ask about 3.2? Yeah, we can do 3.2. 3.2 is not on the quiz today, but it will be on the final exam. Number 14. Right, you guys, I'll have this here before, I'll give you a minute to finish writing it. You guys all set? Okay. So this is chapter 3.2, question 14. All right, so this one says we want to find the area between the curves of x equals y squared and y equals x squared. All right, so first thing I'm going to do is I can solve this in terms of dy or dx. It doesn't matter. I'm biased towards basically dx because whatever. So this right here, I'm going to solve this for y equals radical x. This is plus or minus radical x. So let's go ahead and just plot this out so we can visualize. 1, 2, 2. All right, so here. Here's our first parabola. This is y equals x squared. And then x equals y squared is going to go like this. It's basically the same shape, only floating this way. And so the region that we're looking for is this little bit right here. Okay, but I needed to do this part. But since we're doing this region here, that basically we're looking at the positive aspect of it. Quadrant 1 is just plain old radical x is y. Okay, so and it looks like we're going to go, where do they intersect each other? Right, so I'm going to set them equal to each other. So this is going to be x squared equals radical x, right? And then basically I'm looking at they intersect at x is equal to 1 and x is equal to 0. So that's going to give me my bounds of integration. So I'm going to go, my top function is right here. So from 0 to 1, my top function. So that's radical x minus my bottom function, x squared. Okay. So I can 0 to 1, this is x to the 1/2 dx minus 0 to 1 x squared dx. And now I can just do the power rule, right? So that's going to be 1/2 plus 1, 3/2, all over 3/2, going from 0 to 1, minus 1/3 x cubed, going from 0 to 1. So this is 2/3 x to the 3/2 minus 1/3 x cubed from 0 to 1. Now we plug in our fundamental theorem of calculus. 2/3 1 to the 3/2 minus 1/3 1 cubed. And I'll plug in the 0 just so you can see it. 2/3 0 to the 3/2 minus 1/3 0 cubed. This part goes off to 0. So this is really 2/3 minus 1/3, which is just 1/3. Okay. I have office hours today too, if you guys wanted to come and ask any questions. Also wanted to mention too that the university has opened up the trace reports. Trace reports are our online review of the class. I encourage you, if you felt like you learned new things and you liked my teaching style, please go up on Trace Report and say so, write positive things about that. Also, if you have constructive criticism for how I can do this class better in the future, I would be appreciative of hearing about that as well. So feel free to go ahead and do that. The department does look at those, so it's always great to hear your feedback on that. Anyway, don't forget, you guys, we have a quiz this afternoon on chapter 2. It opens up at noon today. So please take a look for that. Also, please take a look on our Canvas page for next week, the modules page for next week. I posted a whole bunch of old final exams. So please take a look at those over the weekend. Okay. All right, you guys. I'm gonna let you go early. So you can come to office hours if you have other questions. If you want to ask them there, it's totally fine. Okay.
Thank you.
Hey, you guys have a great day.
Thank you.
Take it easy.
Thank you.
Bye.
Thank you.
Take care.